Our project is CLEAR, sponsored by VoltServer, which stands for Colored LED Event Automated Reader. Our technical directors are Camilo Giraldo and Nate Roth, with assistance from Consulting Technical Director Mike Smith. Our team comprises of 2 electrical engineering majors, myself and Nicholas Hatzies, and 2 computer engineers, Toby Awale and John Mendez. VoltServer is based in East Greenwich, Rhode Island, and they are most known for developing and delivering digital electricity, which is a safe and innovative power distribution platform. Our goal of the project is to create a TX550 mountable sensor system that can view, analyze, and decipher RGB status LEDs and blink sequences incorporated in VoltServer's products. This will eliminate the need for a technician to tediously manually decipher them. Being able to redistribute a technician's manpower would save VoltServer time and money by automating the process. Given how commonplace LEDs are used to convey diagnostic info, this could eventually optimize end-of-line testing and quality assurance in a multitude of products. Meeting our ABO would mean delivering a working, enclosed prototype, including the mounting hardware to fit it with VoltServer's TX550 product line. This would include providing all required circuit, code, and assembly files, along with a complete bill of materials and a user manual. While the ABO was not completely met, we were very close. Currently, the prototype hardware is semi-functional, with a new revision of the prototype PCB being needed to correct issues with the DC-to-DC converters and the JTAG interface when connecting to the CCS load programming tool. However, our light sensing circuit is fully functional in its development board form, and the GUI, LED on-off detection, and color identification aspects have been tested and completed. The only algorithm still in its development phase is the blink and blink sequence detection. The enclosure with TX550 mounting solution prototype works, and the user manual is complete up to the latest status of the project. Including and in addition to what was just mentioned in the previous slide, this is the list of team technical accomplishments achieved on this project, which will be discussed in more detail during this presentation. This is a block diagram of how the overall product will function. I will mostly be talking about the LED sensors and sensing array aspect. This is a list of my key technical contributions. While I collaborated on other aspects of the project with my teammates, these are the main areas I worked on individually that I will be discussing in the next section. My main contributions was the overall light sensing circuit design for the prototype. After testing over 20 different photodiode and phototransistor sensors of varying wavelength ranges, I chose a 2x3 sensor grid array design consisting of 6 Kingbright APS5130PD7C-P22 all-in-one photodiode sensors with 1 in each grid. The 2x3 size of the grid was chosen for the optimal viewing slot size to work with the TX550's status LED placement. The all-in-one sensor was chosen for its extremely distinct results when responding to specific light colors compared to other sensors, and the design benefits provided by having the sensors for each color all in the same package. The sensor's photocurrent response, and therefore its voltage taken over the load resistor, increases at varying rates based on the light source's illuminance level and the spectral wavelength emitted on each sensor. How my particular circuit design works is that the voltages are taken over the load resistors connected to each sensor's red, green, and blue individual parts, so 3 signals per sensor from 6 sensors total. All 6 of each color's voltage signals are funneled into an extra low resistance 6x1 multiplexer, where one sensor in its entirety is read in a single instance and each sensor is cycled through. Hence, there is 1 red sensor multiplexer, 1 green multiplexer, and 1 blue. From the 3 multiplexers, the signals are sent through analog devices AD8244BRMZ-R7 JFET amplifier, acting as a unity gain buffer for each isolated signal channel to the microcontroller. All the sensors tested this semester were tested under both dark and ambient conditions across varying distances of 1, 1.5, and 2 inches between the LEDs and the sensor. Our mounting solution hardware, which will be discussed later in this presentation, eliminated the need for the 1.5-inch, 2-inch, and ambient light data to be used. Therefore, these graphs represent the average sensor response to each colored LED under dark or no light 1-inch conditions. The load resistors for each sensor part are 10 megaohm, 20 megaohm, and 5 megaohm for the red, green, and blue sensors respectively, in order to keep the voltages sensed under the microcontroller's max of 3.3 volts while still being large enough to be distinguishable from noise. From this data, the light intensity ratios for each sensor part's response to each colored LED were calculated to use in our algorithms. As you can see from the graphs, the red sensor part responds with the highest intensity to the red LED, and the green sensor part responds the most to the green LED. The green sensor part also responds slightly more than the blue part to the blue LED, but this is due to the respective load resistor value differences of 20 megaohm and 5 megaohm. These response patterns were still distinct enough for our LED on-off and color detection algorithms to work. Sample equations for how these ratios were calculated for the red LED can be seen on the current slide, with similar calculations being done for the green and blue light intensity ratios. I also designed the enclosure for our prototype PCB using Fusion 360 that features a viewing slot for the sensor array and mounting brackets to connect to the TX550 mounting solution that my teammate John Mendez will discuss later in this presentation. Finally, I created the product user manual to go along with the prototype, which includes the testing procedure, product diagrams, operating conditions and instructions, and the bill of materials. My teammate Nicholas Hatzies will be discussing the printed circuit board progress us electrical engineers have made, including a sensor test PCB and the prototype PCB.
While I collaborated with the team on many parts of this project this past year, here are the technical accomplishments that I reached individually. I created the schematic for a test PCB and the first development into a prototype PCB. Along with developing both PCBs came components research and selection, data collection, and developing a user manual. Here is the schematic for the test PCB. The test PCB contains 12 photodiodes, 12 resistors, and 3 switches. The switches were used in order to test each color-specific diode individually or together. The photodiodes were also connected in reverse bias. The test PCB was 4 inches by 4 inches and conducted of 2 layers. There was a top layer and a ground layer. General pad sizes were chosen for the resistors in order to allow testing with various resistor values. A 3D printed holder was also created in order to keep the LEDs a specific distance from the photodiode while taking data. This PCB was very important because it allowed the team to decide on a sensor that would be used on the prototype PCB, as long as gain data that would be used in the software. Now that we have talked about the test PCB, we can talk about the prototype PCB. The prototype PCB used the all-in-one photodiode by Kingbright. Each all-in-one sensor had a red, green, and blue sensor. This allowed for the PCB to have 18 sensors total. The sensors were then sent into multiplexers. There are 3 multiplexers designated by U7, U8, and U9. There is 1 multiplexer for each color on the photodiode. In order to amplify the signal and create enough impedance, an op-amp was needed. The op-amp that was decided on was by analog devices. The op-amp takes the signals from the multiplexers and sends it into analog inputs on the microcontroller. In order to monitor the temperature on the PCB, 3 temperature sensors, which are designated as U1, U2, and U3, were used. The temperature sensors are also sent into analog inputs on the microcontroller. The microcontroller that was used is from the PIC family. The signals from the op-amp are being sent into the microcontroller as seen by net labels red, blue, and green. The microcontroller sends out signals in order to control the switching of the multiplexers, seen as S1, S2, and S3. A JTAG is used to program the microcontroller, which is designated by K1. In order to retrieve the data, there is a level converter, designated by U5, which is connected to a DB9 serial port. In order to power the circuit, there are 2 options, a DC port or a 9-volt battery connector. The power is then supposed to be sent through 2 DC to DC converters, to give 5 volts and to give 3.3 volts. However, for the first design of the prototype PCB, the footprint was incorrect, so the converters did not work. The changes for the second development of the prototype PCB was to use the max 1626 converters instead of the 1627 converters. This would allow for the board to have both 5 volts and 3.3 volts. The prototype PCB was 6 layers and was 2.25 inches by 2.5. The top layer had the 6 photodiodes in the middle, and the backside had the components, such as the microcontroller. I would now like to introduce my teammate, John Mendez, who will be discussing the progress the computer engineers have made.
These are the following areas where I have provided key technical contributions while working on the CLEAR project. When the team began testing several sensors on a breadboard, it was discovered that it was difficult keeping the LEDs steady as well as a fixed distance to collect consistent measurements. Light intensity is defined as the rate of photons that is sensed by the photoelectric device. Therefore, any slight changes in the distance or in the angle of which the LED was aimed towards the sensor drastically impacts the light intensity observed by the sensor, which would be reflected in our measurements. For testing, the team developed LED mounts using two different materials, black filament and clear resin. While creating the sensor profile, the indicated measurement was modified so that the distance between the LED and the sensor would be approximately 1 inch, 1.5 inch, and 2 inches. In all, 6 different LED mounts were used. Once profiling the sensor was finished, it was observed that dark conditions were optimal in detecting an LED and identifying its color. A two-part mounting solution was designed to create a dark channel which would remove all ambient lighting that could possibly affect the light being observed by the sensors. Displayed here is an image of the full assembly. It can be observed how the PCB enclosure created by my teammate Kelsey would be connected to the mounting solution I designed. Displayed here is the workflow diagram for the LED on and off and color identification algorithm. First, the ADC module takes a measurement of the voltage found across each output resistor connected to the colored channels of the sensor. From the sensor characterization, several trends were observed when exposing the sensor to the three colored LEDs. The trends were implemented into the algorithm as shown in the chart. Once the algorithms were implemented, this circuit shown was used to test the program. In the image, it can be observed how each colored channel was connected to a resistor. The voltage follower op-amp configuration takes the voltage found across the three resistors and is then connected to the three pins found on the microcontroller, which would be converted by the ADC module. I was responsible for the layout of the graphical user interface. To grant the user a level of customization, the user has the ability to specify the COM port settings as specified in this section. Once the communication connection has been established, the received data can be found in this section indicated. The LED status and sensor array features were added to accommodate the user. The sensor array heat map serves as a visual representation to the user of what the sensor array is viewing. If it has been determined that an LED is on, the sensor array background will change to the corresponding color as depicted in the images. I will now introduce you to Toby Awalai, who will give more information about the LED status feature and provide an in-depth explanation of the communication program.
Currently displayed on screen are some of my key technical contributions to this project. I worked mainly on making sure there was communication between the microcontroller on the main PCB and the graphical user interface. On the graphical user interface, I worked on the LED status section. I developed an algorithm to decode the raw voltage data that was being received by the user interface. This data was used to determine the status of the LED that was currently being viewed by the sensor head. The slide below shows the different case scenarios for the LED status and the data that was received to realize these cases. The overall system makes use of a serial RS-232 cable to connect to the user's personal computer, and Universal Asynchronous Receiver and Transmitter, also known as UART, was configured on the microcontroller. I made use of the datasheet to determine what pins were used to send or receive data through UART. After selecting what pins I wanted to use, I set the baud rate to meet the requirement for the project, and I redirected the print statement on the microcontroller to go through UART. One of the requirements of the project was to make use of a debugging tool for serial communication. So I implemented the POTIS command line interface to see what data I was transmitting before it got to the user interface. This slide shows the pin view of the microcontroller with the transmitter pin 47 and the receiver pin 46 highlighted in green to the right of the screen. Our team would like to thank everyone that has helped us throughout this project. We would like to thank our technical directors, Camilo Geraldo, Nate Roth, as well as our consulting technical director, Mike Smith, for steering us towards the right path during this project. Lastly, we would like to thank our Capstone Program Director, Dr. Arish Sunak, for giving each designer the opportunity to demonstrate their skill in the real-world environment. Thank you.